I'm good. Yeah.
All right, everyone. So let's proceed with Arvin, who's going to tell us about Timelike separated quantum extremal surfaces in the black hole interior. Sounds scary.
Yeah, thanks. I'm going to tell you about the work that's very much in progress with Neda Engelhardt and Jeff Pennington. So, things are in flux, and I think today will mostly be able to ask some questions and give, if any, very limited answers. Okay, so a big picture idea in ADS-CFT is that there's some sort of a bulk to boundary map, which in some sense can be read off from the geometry of the appropriate bulk slice. So this is the kind of thing that tensor networks are a great model for to make concrete. So, this is the work of many other people, but just to give you an idea of what I mean, for example, if you consider the t=0 slice of the ADS-Schwarzschild geometry and draw a tensor network or a quantum circuit that resembles that geometry, you can get some sense for why, for example, the entropy of the boundary is given, some sort of Hilbert space understanding for why the entropy of the boundary is given by the area of the horizon, or why the left and right side of the bulk, left and right side of the horizon are embedded on the left and right boundaries. This kind of idea has been extended by many people to discuss complexity. For example, if you consider time evolving the state, the thermal field level state to some later state, if you believe that the tensor network continue tracking the maximal volume slice, then there's this independent expectation on the boundary that the complexity of the state will grow linearly in time with a coefficient that's roughly the black hole entropy. And that will be satisfied by the fact that the tensor network, the number of gates on the tensor network will grow like volume, which also grows linearly with time with a coefficient that's roughly the entropy of the black hole. Okay, so this is great, but these are examples of black hole. This is the example of a black hole geometry with one quantum extremal surface that's homologous to the right boundary. Now, in quantum gravity, a lot of non-trivial features of the bulk to boundary map has to do with geometries that have multiple extremal surfaces, multiple quantum extremal surfaces in general. So a geometry that looks like this, or a one-sided black hole geometry that looks like that. This is the kind of geometry, for example, present if you think about evaporating black holes. And the peculiar feature of the bulk to boundary map is, there are probably many, but some to mention is that orthogonal, semi-classically orthogonal states map to boundary states with small overlaps in a way that has drastic consequences if you consider too many bulk states at once. Another peculiar feature that's going to be more important in my talk, it's going to be very important in my talk, is that this map has been conjectured to have exponentially large complexity with an exponent that's given precisely in terms of the areas, or more generally, the generalized entropy of the quantum extremal surfaces involved. So that's the Python's lunch conjecture, that simple bulk operators in the interior have exponentially complex boundary duals. It was given by these people, and since it's going to be important for my talk, I'm going to explain it in one page. It's a relatively easy idea to explain. Okay, so what the authors do is they represent this geometry into in tensor network language by, okay, so let's imagine you want to embed the state of some qubit psi in the black hole interior into the boundary. You feed it into a tensor along with a bunch of other qubits representing this large area of the black hole at the bulge. And to represent the congestion on the way out presented by the throat, they get rid of some qubits on the way out by post-selecting them to a specific out state, the state 0. Therefore, there is the correspondence between these two pictures is that the number of qubits that are being post-selected is given by the drop in the generalized entropy between the bulge and the throat quantum extremal surfaces. Okay, so the explanation behind the exponentially large complexity is that, so if you look at this, if the volume of the black hole isn't large, the number of gates that appear in this tensor network are actually not that many. There's some like volume worth of gates. But the authors explained that that post-selection is responsible for adding an exponential for giving an exponential enhancement to complexity given by the number of these qubits. And one way to intuitively see that is that think of complexity as the number of simple operations you need to do to perform this isometry. This is an approximate isometric embedding of psi into the boundary. And you can't quite do post-selection, but you can do measurements. But the probability of getting the specific outcome is exponentially suppressed in the number of qubits involved. So to get a good probability of success, you need to run this tensor an exponentially many number of times with an exponent given by this, by the number of qubits that you're being post-selected. So it's, as I said, that's so that the main insight here is the correspondence between these two pictures is that the drop in the generalized entropy between these two extremal surfaces is what determines the number of these post-selected legs. So the conjecture, Python's large conjecture, is that in a geometry like this, the complexity of reconstructing the state psi in the black hole interior has an exponential factor, which is given by the drop in the generalized entropy. And they also argue that there's a factor of 1/2 that can be, you can reduce the complexity by a factor of 1/2 in the exponent if you employ a version of Grover search algorithm. So that it's better than the stupid trial and error measurement. Okay, so the motivation behind this, like one of the main motivation behind this work was to match the independent expectations from toy models of black hole evaporation, that reconstructing the interior from the radiation around the page time is an exponentially complex task. This wasn't quite working well with the complexity volume correspondence because the volume of the black hole around the page time is not exponentially large. So this is and by improving the model, the geometric dictionary for complexity this way, you get matches. So that's a very nice success story, and it brings in quantum extremal surfaces, which we sort of feel like they have some interesting role in holography into the game. So I'm going to assume that this sort of structure works, that this sort of idea of mapping geometry to tensor networks and interpreting post-selection at large complexity works. Okay. So this is one example of a geometry, of a black hole geometry with multiple extremal surfaces. And what Nera, Jeff, and I would like to understand, or would like to ask at least, is what's the most possible black hole interior geometry in terms of the patterns of the quantum extremal surfaces involved? In particular, we want to understand if it's possible to have quantum extremal surfaces, let's say deep in the black hole interior, compact quantum extremal surfaces homologous to this whole boundary, that are time-like separated from each other, at least in part. The motivation behind wanting to ask that question is that if that kind of thing presents itself, it's no longer clear how you should interpret those how you should map the pattern of the quantum extremal surfaces in the geometry into a tensor network that creates the isometry. So if you can come up with the right map, you'll be forced to learn something about time evolution within the Willard-DeWitt patch of the bulk. Now, I don't think we quite have the answers, but that's the motivation. Oh, I should say here that this is sounds a little bit related to some other question, which is if you consider simultaneously two different, let's say, boundary subregions, then their RT surfaces could be time-like separated from each other. I'm not quite sure if they're fully related, but all I can say is that instinctively, for me, this seems like a more fundamental issue, because even if you're considering entanglement wedge reconstruction within one boundary region, this issue presents itself. Whereas in the other case, you could imagine that so long as you consider one boundary region and say its complement, there exists a canonical tensor network representation. Yes, who asked? Oh, man.
When you say time-like separated QESs, do these have to be minimal, or are you talking about?
No, non-minimal quantum extremal surfaces, but yeah, like the bulge and the bulge and the throat in this example aren't minimal quantum extremal surfaces, but the minimal one is, oh, it's actually, sorry, here. Well, yeah, the empty surface is the minimal one here, but yeah, so extremal, but non-minimal necessarily. Okay. I mean, the minimal is just one of them, right? So.
Yeah.
So the minimal one could be time-like separate from some other one. Chris?
Yeah, it sounds like you're motivating it by trying to understand the tensor network that describes the time slip. I would have said that even in the original setting, it was sort of a cheat to motivate it with a tensor network, because you can't really describe the maximal volume slice with a tensor network because like the RT surface won't lie.
Right. So the map to figure out exactly what the map is, the more general map, the bulk to boundary map has to do with the whole Wheeler-DeWitt patch. But the concrete thing I want to say here is like, so if you want to ask, for example, one concrete question about the map, you know, that's not like, okay, let's figure out the tensor network, is like, what is the complexity formula? The Python's lunch conjecture, as I stated, is ill-defined when that kind of thing happens. And I think if you come up with the right complexity formula, it's inevitable to not have a correspondence between that and some sort of bulk to boundary map, because what's the motivation for the complexity? So yeah.
Sounds good, thanks.
Okay. Okay. Okay, along the way, I'm going to also discuss a natural classification of quantum extremal surfaces that comes about when thinking about this. Okay. Okay, so let's start with actually some of the simpler things. So we're talking about black holes. The defining feature of black holes is the existence of horizons. So here I've shown them with H plus and H minus. Now it's been shown, assuming the quantum focusing conjecture, that quantum extremal surfaces cannot stick out of either of the horizons. So they need to stay in this region behind. So we are interested in the pattern of quantum extremal surfaces. It makes sense to ask, where is the first quantum extremal surface that you encounter? It actually makes sense to define a notion of an outermost quantum extremal surface as a quantum extremal surface which is contained in the outer wedges of all other quantum extremal surfaces homologous to that boundary. Where an outer wedge of a surface is defined as the domain of dependence of its homology slice. So here I have a black hole spacetime and I have a surface gamma, and its homology slice is this, and the purple is the outer wedge. So outermost QES is one that's contained the outer wedge of all other QESs. It makes sense to define this. It's non-trivial to prove that actually an outermost quantum extremal surface always exists in a geometry satisfying the quantum focusing conjecture. If you were just given some arbitrary Lorentzian geometry with no restrictions on it, you could imagine a situation where you have quantum extremal surfaces, or if you want classical extremal surfaces, if you're in the classical regime, like chi1 and chi2 that are furthest out in a sense, but neither one of them is outside the other. They could be time-like separated, or it could be partially time-like, partially space-like separated, or fully space-like separated by like this. But you can rule this out assuming quantum focusing conjecture. So an outermost quantum extremal surface is uniquely defined. The proof is a little bit complicated in the most general case, but it's very easy to explain in a case, for example, where they're fully time-like separated from each other here, like here. There you just intersect their outer wedges and argue by quantum focusing that the sphere there has negative expansion in both directions. And it's a bit of work to show that if you perform a restricted maximum in this wedge, subject to that condition, the outcome will not get stuck on the boundaries, therefore will be an extremal surface within the meat of the wedge. And then therefore, if this happens, there is something further out. Okay, so that's nice. So we are interested in a pattern of quantum extremal surfaces and time-like separation, and the outermost one doesn't have that problem. The outermost one is free of quantum extremal surfaces, time-like separated from it. Okay, so if chi, so I'm showing the outermost with chi here. If chi was the minimal generalized entropy quantum extremal surface, that's it. That's the end of the entanglement wedge, relatively boring entanglement wedge. But if the minimal SGen was further in, like I've shown in E here, then the simplest next possibility is to have three quantum extremal surfaces, E, chi, and a bulge quantum extremal surface B. So this is like the lunch situation I explained before. But geometrically, the way we know that a quantum extremal surface B needs to exist is through this nice restricted maxi-minimax prescription, which was given in the original Python's lunch paper. And I'll explain that a little bit since it'll be a bit important. So that prescription, so E and chi's are throats. And the prescription is to take this red wedge, the region in between them, divide it up to all Cauchy slices. Within each Cauchy slice, consider all possible foliations. So I have one Cauchy slice and I'm foliating it from E to chi. Within that foliation, pick the maximum generalized entropy slice, minimize that over various choices of foliation you had, and then like the max of maximum, maximize that over various choices of Cauchy slices. So the outcome of that was argued to have a quantum, would return a bulge quantum extremal surface, B, with generalized entropy larger than both E and chi. That's because of the max step here. Okay, so from here, it's a pretty straightforward argument to generalize this to case of the most general space-like separated quantum extremal surfaces. That would just be a case where you have multiple lunches in series, all quantum extremal surfaces space-like separated from each other. I just want to make a few points with that, so I'll just explain those few points with the case of a double lunch. So there are actually two qualitatively different double lunch scenarios, which I've shown here and here. So in the first double lunch scenario, each lunch by itself is an approximate isometry. So think about the tensor network representation again. In each lunch, I'm adding more qubits than post-selecting. So for example, if I'm interested in complexity of an operator at P1, I just can run both of these isometries. So the complexity is just dominated by the bigger complexity of the two. So it's given, the exponent in the complexity is given by the biggest drop of generalized entropy in the quantum extremal surfaces, either here or here. But note that if I want to reconstruct P2, I don't need to refer to this region at all. I can just write the isometry from here outwards. I can just do that isometry. Therefore, the complexity is just dependent on this piece of the geometry. So this is happening because gamma 3 is an outer minimal quantum extremal surface. It's a quantum extremal surface such that that doesn't have any other quantum extremal surfaces out in its exterior with smaller generalized entropy. Okay, so the other case is the case where the second piece is not an isometry by itself. And there, to reconstruct P1 or P2, either one, I need to run the whole thing. And it's a little bit more work to show what the right complexity formula is. But it ends up similar to before, meaning that it's given by the biggest net drop in generalized entropy through the circuit, which in this diagram is either here or here. Okay, so these all can be put together in a general rule for the most general space-like separated quantum extremal surfaces, which is some messy equation, some formula you can write down. I just emphasize the important part of it, which is that given an operator P that you want to reconstruct, you do a minimization over all outer minimal wedges. All quantum extremal surfaces such that in their exterior, there's no quantum extremal surface with smaller generalized entropy. And within each outer minimal wedge, like I've shown in red here, the procedure is you look at all throats, you do max and minimax between the throat and the outer minimal quantum extremal surface, you find the appropriate bulge, you maximize over the throat, and like I said at the beginning, you minimize over outer minimal quantum extremal surface. Okay, so this is some formula I can write down, the most general space-like separated case. Okay, so now I'm going to start saying that maybe some things that we know about the time-like separated thing. But before that, I wanted to actually, so these are toy models. So it's kind of important to, whenever we get a chance, to match it to an independent, for example, we have some formula for complexity. It's good to have an independent boundary argument whenever we can get it. And so far, for these kind of setups that I discussed, I claim there are boundary arguments. So I'm just going to say some words about that, not get into details. So for example, a prediction of the outermost, like a basic prediction of Python's lunch conjecture is that the outermost quantum extremal surface is not exponentially complex. It's simple. And that's been argued for in some papers going back to an earlier conjecture made by Aaron and Neda. And their argument roughly goes like this. It's just that the outermost quantum extremal wedge can be, the argument is that it can be accessed. The claim is that it can be accessed by performing by boundary time evolution plus simple sources that push the horizon out and limit it to the outermost quantum extremal wedge. So therefore, reconstruction within the outermost quantum extremal surface is a sophisticated version of HKLL, which only involves time evolution on the boundary, and therefore expected to be polynomially complex because the amount of time evolution isn't large. And the best argument for the single lunch case is the toy models of black hole evaporation, which was the original motivation of these people to match the complexity to these black hole evaporation toy models. So I'm calling that a boundary argument since the toy models sort of discussed what's happening on the boundary. And even these stupid multiple line scenarios also show up in some interesting boundary states. So there are this interesting states discussed by Boland, Pfefferman, and Vazirani, where they're discussing boundary states, but the bulk dual of what they're discussing is a black hole microstate, say, formed by collapse, which you then act with random unitaries on every scrambling time or so. The bulk dual of that geometry is a multiple line scenario with all space-like separated quantum extremal surfaces. And again, there's a matching complexity. So, okay, now I'm sort of, we're going to go into the dark a little bit now, because the regime of time-like separated quantum extremal surfaces is a regime where precisely, and this is one of my bigger questions, is a regime where we don't have quite this boundary side. I don't know how to take a black hole geometry, do some physically understandable things with it, couple it to some reservoir, act with some unitaries to get time-like separated quantum extremal surfaces. So we are a little bit in the dark. Any questions so far? Okay. So what can happen in a general black hole interior? Can we have quantum extremal surfaces like mu1 and mu2 that are time-like separated from each other or from the RT surface? For a while, we were thinking that maybe the Python's launch conjecture is a hint that this can't happen. Looking for a proof, didn't work. Until we found an explicit counterexample. We started finding explicit solutions. So I think there's actually something instructive maybe about the counterexamples. So I'm going to discuss that. But before that, I'm going to take a little detour and discuss the classification of quantum extremal surfaces that comes about naturally when thinking about this. So I've been saying like throats and bulges an inappropriate number of times. What are these? Like, are they, what classification do these belong to? So it turns out, if you think about it, right, that there's naturally three class of quantum extremal surfaces. So here I'm going to, for now, focus on spherically symmetric or transverse symmetric quantum extremal surfaces. So these dots are all quantum extremal surfaces, and I have this time and space direction away from them. Since these are quantum extremal surfaces, the first derivative of generalized entropy is 0. So the natural way to classify is to look at the second derivative. Then throats are quantum extremal surfaces which have a positive a range of positive second derivatives in the spatial direction. Bulges are quantum extremal surfaces that have no positive direction. And bounces, what we call the third category of bounce, is a quantum extremal surface that has a range of positive second derivatives in the time-like direction. So these are sort of, yes. They could be anything. I mean, they just shouldn't get super close to the null, because we know at null by quantum focusing they're negative.
So you're saying these are always space-like and these are always time-like?
Yes. Yes. So we believe that these three categories are fundamental, though it's taken us a while to pin down the correct definition, quite the right definition in terms of quantum extremal surfaces. There's some candidates it's taken us a while to find the right one. We believe this is the case. If you want to have a marker for what the classification in general is, just have something to work with right now, think of this as quantum extremal surfaces that can be returned by a maximum procedure. These as quantum extremal surfaces that can be returned by minimax procedure, and these as quantum extremal surfaces that cannot be returned by either. The point being that there is something in that category. So throats are by far the best understood, the most studied examples of quantum extremal surfaces in ADS-CFT. And boundary of the entanglement wedge is a throat. Outermost quantum extremal surface is the throat. Outer minimal quantum extremal surface is the throat.
Max for the bulge. I'm just repeating the question.
This is the covariant. This is the covariant general formula. I mean, if you have a spatial, if you have, like, let's say, some higher dimensional sphere in some slice, there is always a way to change that to increase the area, right? Like I've given this formula in the spherically symmetric case, right? So the thing needs to be more sophisticated. Okay, so throats is the most well-studied example, and it shows up in a bunch of concrete formulas in ADS-CFT. Bulges now show up in complexity formulas. If you want to have an example of a bulge in mind, if you insert a massive particle in the behind thermofield double by inserting in the Euclidean path integral so that the horizons separate, you get a bulge extremal surface in the middle. Bounces are a little bit more mysterious. Just the de Sitter horizon is a bounce. The inner horizon of Reiser-Nordstrom is a bounce. That's a dodgy area of space-time, but just imagine as a local solution to Einstein field equation, it's a bounce. If you want to have an idea of a non-spherical symmetric bounce, think the inner horizon of Kerr. So they can even come about without matter.
So I have a question.
Yes.
So general quantum extremal surfaces are very bad. I mean, I just know from having suffered with them, they can be self-intersecting. They don't have to be acausal. So
Sorry.
is there some?
They don't have to be acausal.
No, certainly. Yeah. If they're self-intersecting, right? I mean,
Sorry. No. Yeah. Well, you
Yeah.
need to define generalized. You need to assign generalized entropies to them. To it, right? So self-intersecting, right? Self-intersecting is possible.
Yes.
I believe that in all examples where you have self-intersecting classical ones,
Yeah.
the quantum extremal surface will separate, will pinch
No,
up.
of course, the quantum extremal surface doesn't have all these pathologies.
Oh, I see.
Because it's minimal. But as soon as you consider things that are
No. General quantum extremal surface. Quantum extremal, but not like locally extremal, but not minimal.
yeah, that's what I'm talking about. If the only condition is local extremality, then lots of bad things can happen. What I was wondering is, if in some sense, all those bad things only happen for the bounce, but not for bulge. I mean, throat, I know.
No. If you did there's this intersecting thing that you're talking
Yeah.
about, for example,
Yeah.
again, at the classical level does happen for a bulge, for example. Now, if you want to think about it, like imagine.
Okay, so even for the bulge that, oh yeah, I guess like with the two interval thing,
Yes,
right?
yes,
Yeah,
yes. But even that
Yeah.
might, so some things you need to be careful. Yeah. Even there, I believe if you include quantum corrections, if you find a quantum extremal surface, it will pinch up.
Mhm.
It will not stay like that. But yeah, so since I'm focusing here on spherically symmetric ones for now, and part of the difficulty in finding the right definition is to exactly realize if you are, what kind of restrictions do you want to make? Yeah, do you want to allow for like immersed manifolds or just embedded manifolds and things like that? That's part of the difficulty of generalizing it. But so far, it looks like when you include quantum corrections, actually they all become embedded submanifolds, even though the classical versions are immersed.
And also acausal manifolds.
Acausal, I don't understand, because how do you assign generalized entropy if they're acausal?
Well, okay, it's true. I guess I only know how to do that for the area.
Yeah, for the area, yeah.
I think a more natural object in many situations, including I think the one you're asking about, then the surface is the wedge. So think about the 4-dimension, the whatever, 0 codimension region that the relevant surface is the edge of. And then I think the causal problem that you're worried about is similar to the self-intersections. And presumably may have a quantum resolution along the same lines. That would be my hope.
Historically, we would have said being globally minimal is the thing that gets rid of all the bad things, but now we're trying to go beyond that. So.
Okay. So what else do I want to say about this? Okay. Okay. So bounces so far don't show up in quite a number that we can calculate on the boundary. Okay. So now let me discuss the explicit construction of what we think are time-like separated quantum extremal surfaces. So this involves coming up with a specific solution of a gravitational constraint equation on a time-symmetric spatial slice, like I've shown in red here. So this is some initial data surface. So here I say QES is, I'm talking about classical extremality here, and I don't think quantum corrections matter much. So there will be quantum extremal surfaces too. So what I want this initial data surface, what the feature I wanted to have is, I wanted to have two throats, mu1 and mu3, and a bounce in between. So this, I'm gonna take this to be time reflection symmetric and also left-right symmetric about mu2. If you arrange this solution and you evolve it to the future and the past, you get a whole space-time. Then think about running a max-minimax procedure between mu1 and mu3. The max-minimax prescription needs to return a surface. However, the surface cannot be a bounce. A bounce cannot, can provably in this case, not be returned by max and minimax. And since there is no other quantum extremal surfaces or classical extremal surfaces on the slice, the classical extremal surface needs to be off of the slice. And by time symmetry, it needs to be time-like separated from each other.
I'm sorry if I missed it, but did you give any examples of bounces? It's like de Sitter space.
The Sitter, inner horizon of Rice and Nordstrom, inner horizon of Kerr.
I'm sorry. Yeah. So you're cutting out a piece of de Sitter and pasting it in or something like that?
Well, not quite de Sitter here. Actually, yeah. So what's morally similar. The explicit, so this is a general idea. The explicit construction we make is in JT gravity plus matter. And what we do, we just satisfy the constraint equations there on a spatial slice. And the property of that solution is the matter is some massive scalar field. And we turn it on, turn that massive scalar field here and turn it off appropriately outside where the geometry is just ADS Schwarzschild. And we make sure that the constraint equations are satisfied and we have a bounce. And when we evolve it to the future and the past, we get these singularities, or phi goes to negative infinity, and these bulges show up. These are bulge type quantum, classical extremal surfaces. So something related to your de Sitter comment is, by the way, here some comment about this. I'm explicitly ignoring the possibility of having an asymptotic time-like de Sitter type boundary. That makes many things confusing. It makes maximum confusing. I'm just not allowing that. And having a scalar field profile here will cause, when you evolve it off of the slice, will cause lots of focusing and the thing will collapse.
You don't need to violate the strong energy condition, right? Not that that would be a problem, but
that will be violated by massive scalar fields, right?
Well, so I'm confused. You said Rice on Nordstrom is an example?
Yeah. Maxwell also violates.
Oh, I see.
Yeah.
So
People forget that Rice and Nordstrom has matter.
Yeah. So that, I see.
Yeah.
So that is.
But the inner horizon of Kerr is also. So you can get a bounce from lack of spherical symmetry as well. That's because you can't quite set the twist to 0 if you look at it.
So you don't have to violate the SEC.
You don't have to violate that, yes, in general. Okay, I have until 11:30, right? Yeah. Okay. Okay. Okay, so this is an explicit, so this might have stopped looking for a proof that this can't happen. But it's kind of interesting that in this example, all 3 kinds of quantum extremal surfaces show up. We wanted to get 2 bulges or throats to be time-like separated from each other and a bounce pop. I mean, in this way of doing it, just by construction, we introduced the bounce. So we wanted to check if there is some sort of correspondence that goes beyond this. And I don't know the answer to this, but at least in the case of spherical symmetry, you can prove that if you have 2 quantum extremal surfaces, mu1 and mu2, such that mu1 is a throat or a bulge, and mu2 is a throat or a bulge, then their intersection of their past and the future has a bounce quantum extremal surface. So I don't know to what extent this goes beyond spherical symmetry. It's possible that it works in the case where mu1 and mu2 are fully time-like separated from each other, but a little bit more messy. But we don't know. Another related thing you can show in this along the same lines, if you have a bounce whose future wedge ends in a singularity, then there exists a bulge in its future wedge. So for example, therefore, if you have a bounce where it's both future and past has singularities, then there would have to be 2 bulges that are time-like separated from each other. So bounce quantum extremal surfaces don't quite calculate the number in this scenario, but they pop up when you have time-like separated quantum extremal surfaces, weirdly. Okay, so as I said, we don't quite have the answers for what the complexity formula is, but I'll just tell you, just present you with a guess, and this is work in progress. So, okay, so the conclusion so far is that in general, black hole interior is a complete mess as in terms of time-like separation of quantum extremal surface. This is not a problem we can avoid. But we need to understand the bulk to boundary map, or at least the complexity formula, for example. So this guess is motivated by the realization that the outer minimal quantum extremal surface satisfies so the notion of outer minimal quantum extremal surface, remember, was a quantum extremal surface that didn't have any other quantum extremal surface with smaller SGN in its outer wedge. And okay, Ben has a question.
Make sure I understand. If someone tells you that there's time-like separated quantum extremal surfaces, does that necessarily mean they would have been generated from bulges on some, it's in the time symmetric case, from bulges on some
From bounces.
no. Because in the example that you gave, the first example,
Yeah, there was a bounce on mu2, and the bulges were time-like separated from each other.
sorry, yeah, that's what I meant. Yeah. Is that necessarily the case? Like if I just gave you some time-like separated quantum extremal surfaces?
We
did it
proved
tell
this
you-
only for spherical symmetry. I mean, it's a relatively straightforward proof that if you have two surfaces, mu1 and mu2, such that mu1 is a bulge or a throat, mu2 is a bulge or a throat, these are things that actually feed into the tensor network representation of the Python's launch. Then there needs to be a bounce. So if someone tells me the spherical is symmetric and you have two quantum extremal surfaces that are time-like separated of the throat or bulge nature, then yes, I would say it needs to be generated by a bounce, meaning there is a bounce.
Okay.
Sorry, can I ask a dumb question?
Yeah.
So why doesn't the max and minimax just deal with this because the last max is over Cauchy slices, right?
Mhm.
And so won't that max just, I mean, you drew one particular slice
Sorry.
here, but you just
This is not this example is not a particular case where the Python's line formula is in jeopardy. It's just an example of
is there a case where it is? I mean, shouldn't you just pick the worst case? and-
yeah, like if you have throats that are time-like separate. Oh, one thing that I thank you, actually, that reminds me.
Yeah.
There is a similar construction like this given, not following this strategy, but for throats to be quantum extremal surfaces from each other. And if you have a bunch of throats, and so because you need two throats to do max and minimax in between. So
Yeah.
once your throats are time-like separated from each other, then it's no longer clear.
But okay, so the throats are even time. So yeah, because you had this formula for dealing with multiple bulges.
Multiple in a
before
space-like
on a
thing,
s-
yeah.
On a space-like
Yeah.
slice. And yeah, here that you can't put them all in one space-like slice, but you can't find some worst
No.
case space-like slice.
Well, as I say, okay, so in this case, it is possible to just find, so if you have a chain of space-like throats, you can find the appropriate bulge, even if a bunch of bulges are time-like separate from each other with max and minimax, in a sense, find the worst thing or something. But once throats start becoming quantum extremal time-like separate from each other, I've claimed that is no longer possible what you have to do. Like, yeah, maybe some generalization of max and minimax, but what we know so far, I don't think answers it.
Yeah, can you just summarize again, at the end of the day, is everything possible and the only thing that's nailed down is the actual true QES and the outermost one? Or
No, the true QES is not nailed down. That doesn't have to be space-like separate from all other things.
oh wow, that's bad.
No, it's not necessarily bad. A proof of that was given somewhere, but it was wrong. But it's weird, right? Like you want it to be.
Sorry, I thought there are
Outermost is
these
done.
arguments like about the uniqueness of the quantum extremal surface, for example.
It is unique.
No, so sorry, I think I'm misunderstanding what you're saying. So if you have two quantum extremal surfaces that are time-like separated, I thought there's usually a proof that there's a larger one. There's one farther out that you can construct that's more minimal.
If you're fully time-like separated, perhaps that seems pretty easy, but they don't have to be. They could be messy. I mean, you need to look for a robust geometric argument here that allows for partial time-like separation, partial space-like separation.
Yeah, I thought that was our argument. That's what I'm confused about. Sorry.
Sorry, I mean, the proof that I'm most familiar with is the one that's in their unpublished paper.
Oh, I don't know.
And
don't know what's
it uses this prescription that's neither the QES nor the maximum prescription, but that's the one that the generalization of Akers and Yeah.
I don't know if this is quite related to this. There is okay, well, maybe you'll understand when I say this, if it's
But I think
that.
that proof is correct, so.
Well, it is, Arvin, right, that it's very subtle, that they can be partially timelike.
Sure, but that's the whole, that's
I
the whole
don't-
reason why it's a difficult proof.
I don't think it is true that if you have an outer minimal quantum extremal surface, if you have two outer minimal quantum extremal surfaces, that they can't be time-like separated from each other.
Right, but all I was trying to say is, why is this necessarily putting the max description in jeopardy? I would just say you need to do it for the one that's the largest. And everything's spaced like.
Sorry.
I think maybe we can talk about it.
Yeah, I don't quite understand.
I think this is turning into inside baseball, so
Yeah.
let's.
Okay. All right. Okay, so we don't really know what the map. I don't think we know what the map is. I just tell you some property of the outer minimal quantum extremal surface that's nice, which motivates some formula, which might be related to what you were saying. So outer minimal quantum extremal surfaces are ones which have no quantum extremal surface with smaller SGen in their outer wedge. By the way, for those who are familiar, outer minimal quantum extremal surface is an independent definition I gave, but it's equal to the minimar QES. Minimar QES is the same object. This different definitions, but turn out to be the same, which was discussed in the classical case here and then here. Okay, so it turns out that if the idea behind the outer minimal QES is that you can push the reconstruction out to the boundary from them, as I discussed in the tensor network picture, there is a non-trivial check it needs to pass, which is that it needs to be a subset of the entanglement wedge. If it's not a subset of the entanglement wedge, that would be bad for the idea of pushing this, doing bulk reconstruction in it. And you can show, and this might be the thing that you're talking about, you can show that this can't happen. The outer minimal quantum extremal surface needs to be fully embedded inside the entanglement wedge. You can have various outer minimal quantum extremal, I don't know, maybe you guys have an extra proof, I don't know. But we can have outer minimal quantum extremal surfaces that are not fully space-like separated from each other, but that's fine. But they need to at least be contained in the entanglement wedge. So that's a nice geometric consistency check for this idea of taking outer minimal seriously. And another thing is like, okay, you might wonder, so how do we do this kind of bulk reconstruction that doesn't reference the region to the past of an outer minimal quantum extremal surface? So usually for bulk reconstruction, we use a boundary row, some boundary density matrix, which only refers to this region. Now, this is not this is sort of an idea that might have been alluded to in these papers, not quite in the sense of, in terms of bulk reconstruction, but the construction is given in these papers where you can take, so if you take an outer minimal quantum extremal surface and you CPT glue it to itself, you can define a boundary state, you can define a boundary state rho, and so that's the density matrix you can define on the boundary, and you can wonder how does that density matrix act in this space-time, in this state. And presumably it's possible, I don't know, but I think it makes sense to say it acts in this region and it commutes with the things outside. This needs to be checked, but it's a very feasible thing, and that's the kind of thing and it's important here that the surface was quantum outer minimal. So with that, motivated by that, our current guess for the complexity formula is the formula from before, except we are now scanning over all outer minimal quantum extremal surfaces. That could be, for example, time-like separated from each other. So for example, you can have a word line, a bulk observer, and it leaves one outer minimal wedge and it enters an outer minimal wedge, enters another outer minimal wedge, and instantly its bulk to boundary map will change. But this is, since this, I mean, this is a, the messy formula from, it's exactly the messy formula from before, except the outer minimal wedges don't need to nest. So I don't get into it since we don't have a proof of this, but as promised, I'm gonna end with a few more questions than answers. Okay, so a question that I would really like to know the answer to is what kind of boundary state is dual to these kind of situations where you have bulk quantum extremal surfaces that are time-like separated from each other. Like, as I said before, can you form a black hole from collapse and do something physically reasonable to it, couple it to some reservoir, act with some unitaries, do something that produces the time-like separated quantum extremal surfaces? And if not, why not? Here, I should say, you could say, well, who knows if this is there's an interesting boundary dual to this. Here I have I don't know if the answer is yes or no, but one concrete thing I can say about it is that in the evaporating black hole spacetime, something similar happens, not quite time-like separated quantum extremal surfaces, but note that one thing that comes about if you have time-like separated quantum extremal surfaces is that the outer wedges of the quantum extremal surface don't nest, right? That's obviously the case. But outer wedges of quantum extremal surfaces could not nest even if they're fully space-like separated from each other. And that kind of thing I claim happens even in the evaporating black hole spacetime. There are bulges whose outer wedges do not nest. And there it's related, the physics is related to a phase transition in complexity, which causes the complexity of reconstructing an interior from the radiation to be small at the end of evaporation. So that's sort of a hint, a boundary hint for some sort of boundary hint for outer wedges not nesting. And I would like to understand that relation with time-like separation. Okay, so other obvious questions is the role of bounces in ADS-CFT, a concrete quantity that the bounces generalized entropy computes. I feel a little bit like, with all this classification of quantum extremal surfaces and these new formulas, we're a little bit like in a period between RT and Lukowitz-Maldacena, where we have a whole bunch of formulas and they're presumably computable on the boundary concretely, but we're just writing down some guesses, some formulas. And once we understand some sort of a boundary prescription for computing the right thing, these guesses will presumably come out naturally. So making contact with new quantum extremal surfaces, that's the thing. One question related to this, and obviously more related to time-like separation, I would like to understand if fully time-like separated throats or bulges always come with a bounce, if this connection is general. And lastly, I'm just going to leave you with, so I started this with motivating, we don't know where, where is the slice where the tensor network lives. And, and I'm going to end with some concrete words, with some specific example where I can say something about this. So as Daniel alluded to, if in the counter example I made with the two throats and a bounce, where you have these two bulges, it seemed, okay, max and minimax prescription instruct us to consider this pattern, to feed those generalized entropy differences in the tensor network. And note that here there exists a time symmetric slice in the bulk. So there's this lore that maybe if you have a time symmetric slice, that's where the tensor network lives, but there's no contradiction if you have weird situations where you have spontaneous symmetry breaking. But note that if you just look at the intrinsic geometry of this slice, it looks very much like something very much like something you want to call a Python's lunch. So by thinking about this, so either the Python's lunch conjecture is wrong, or if it's right, it's telling you that some intrinsic time-dependent property of the initial slice is important for picking something that you can't read off from the intrinsic geometry, but it's inherently related to time derivatives, is responsible for telling you what the right bulk to boundary map is. So that's just something between these this tensor network lore and the Python's lunch conjecture. But again, the difficulty here is that I don't know how to prepare this state on the boundary independently to check what the complexity needs to be. So we just have two guesses. Chris?
Can Is it because you want that bounce to be the bulge in the Python's lunch?
Well,
You don't want that?
What I mean is, if you go with the lore that the tensor network needs to sit on the time symmetric slice, then you would be forced to consider the bounce as the bulge of the tensor network. But the Python's lunch conjecture is clear on picking bulges, the covariant definition of the bulge, which would ignore this and go for that.
I see. So you want bulges to be on the tensor network.
If the bulge was on tensor, if this was a bulge and you didn't have any other surfaces, it would be clear that they're the same. They would say the same. But if you are faced with a situation where this is a bounce, then there are two different guesses from the tensor network lore and the Python's lunch conjecture.
And so this bounce has greater area than the throats, is that right?
Yes.
I see. So, and do you have a reason to believe that the correct formula isn't just
taking the bounce?
Yeah.
I don't have an independent check. It's just that the Python's lunch conjecture uses, so the only thing that's guaranteed to exist between two throats is a bulge. So that's why in a general covariant rule, it makes sense to do if you do max and minimax, you will find a bulge always, but not necessarily always a bounce. But yeah, I don't have an independent check for what the complexity would be in this case, but I'm just saying the proposal so far says that the time symmetric slice isn't the relevant slice.
Okay.
So I'm just pointing out this tension between these two proposals. I think, I'm biased. I think the rule that always finds a quantum extremal surface, which is the bulge surface, is the right rule even here. And somehow the time direction in the bulk becomes important here in finding the right bulk to boundary map, and skips this and goes with that. Note that this is not a crazy thing. Spontaneous symmetry breaking for where the tensor network lives can happen. It doesn't happen for entropies, because if you have a minimal QES, if you have one time symmetric slice, a minimal QES will always provably live on the time symmetric slice. But now we're talking about many other quantum extremal surfaces, and that no longer needs to happen. Okay, I'll end here. I think
So Arvin, I agree that it's nice that there's this existence proof for the max and minimax, but didn't you tell us earlier in the talk that it's wrong in these situations where the spatial slice has multiple bulges?
No. Why did I say it's wrong? Did I say it's wrong?
Did you? Well, is your Python's, not the theorem of the existence, but the formula, right? You wrote down a formula which was kind of complicated for the case where there are multiple space-like bulges. And can I interpret that formula as just saying, I take the outermost throat and then I take the thing that comes out of max and minimax, and that's going to be right?
No.
I thought it's not right.
No, that's not right.
Okay,
that wasn't that formula.
Yeah.
Yeah, right. So I see, maybe that was related to Adam's comment. It doesn't make sense to go to the outermost and the RT surface and do max and minimax between them. That doesn't give you the right.
That's what I'm saying,
Yeah, but the formula I wrote, I didn't.
Yeah, but
could be right.
Is there a max and minimax type construction of the formula that's actually correct, even in the space-like case? Or
well, it's not like a one-shot max and minimax, but it's like you go to each individual throat, you do various max and minimaxes, and then you maximize over the choice of throats. So it uses max and minimax, but it's not just like one max and minimax.
But you can show that each thing that you need in that formula exists. I guess you have
yes.
to assume
Your
slice, but
sort of definitionally it exists.
Yeah.
Okay. And that formula we have some independent evidence from the boundary in this Paul and Shahbazi-Moghaddam kind of states.
All right, other questions?
Yes.
I don't know if this question makes sense, but in terms of the bulk to boundary map, is there some significance to how time-like separated the quantum extremal surfaces are? Like in terms of the complexity?
I don't know. It's as I said, we don't really have any answers, right? We mostly just asked the question, and I said a few things about the space-time with time-like separated QESs. So the guess that I wrote down that doesn't seem to care about how much time, but how time like separated you are, but I don't have anything concrete to say.
Okay, and just really quickly, when you say you're interested in what state on the boundary is dual to the space-time with these time-like separated QESs, you're talking about the full state, like the fine-grained state of some boundary region, and not just the coarse-grained state for the outer wedge of a specific.
Yeah, no, I'm talking about like,
Yeah.
something like the evaporating black hole
Yeah.
space-time, where you have an outermost, but you consider everything and you get a whole bunch of bulges and throats, but they're all space-like separated there. But
Yeah.
can we make up a situation where they're time-like separated from each other?
But like, since you were saying that time-like separated QESs, they basically are always generated by considering the QESs on some initial data slice.
No. That was just, sorry, I maybe explained it wrong. That was just an explicit construction that made us stop looking for a proof that this can't happen.
Okay, but it's not, okay, asking earlier, but like, if you just know that there are time-like separated QESs, it's not necessarily the case that they're always generated by just considering space-like separated.
No, not by considering not by the only general statement that I could not by considering a time symmetric slice or anything. The only general statements, semi-general statements that I presented were these ones. If you have a general spherically symmetric space-time, not time symmetric, just spherically symmetric, and you have mu1 and mu2 that are throats or bulges that are time-like separated, there will be a bounce in between them.
Okay.
That's a general statement. It doesn't have to do with that specific construction, but it uses spherical symmetry. And another similar statement here, but so bounces sometimes, yeah.
Okay.
If you know you have spherical symmetry, then in the situation that you described, there exists a bounce.
Okay.
Yeah.
Thanks.
Anyone else? Okay, so let's thank Arvin again.